Good afternoon, everyone. I am George Pericini. We are here today to discuss an adiabatic process. I will be demonstrating the energy balance of an adiabatic process. So general energy balance is going to be energy in minus energy out equals the change in internal energy, denoted by delta U. We could also write it in its rate form, E in minus E out equals 0. We can go ahead and put the little dots here. Going forward, we can expand this, say, work in plus Q in, which is heat flow, plus energy due to mass, in minus the same stuff, but out. So work out, heat flow out, energy due to mass out. If we keep it in rate form, that is also equal to 0. Being that we're dealing with an adiabatic process, and we are assuming steady state, we can go ahead and eliminate heat in, mass flow in, heat out, mass flow out, and what we are left with is going to be work in minus work out equals 0 when it's in its rate form. And this is going to be demonstrated being that we have work in minus work out and their rate form is equivalent to 0. We could say work in equals work out rate form, assuming steady state, where work in is equivalent to the potential energy of the pendulum, while work out is a subsequent kinetic energy, which is observed here. This would be our potential energy. When we hold the pendulum, we have potential energy built up here. Once we let it go, this is going to be the kinetic energy due to the gravitational forces that the pendulum is experiencing.
Hi, my name is Kenneth Lee, and I'm going to be giving you a little bit of background knowledge about the pendulum. The pendulum is defined as an object hung from a fixed point that swings back and forth under gravity. Galileo created the pendulum in 1637. However, Christian Huygens is credited with patenting the pendulum in 1657. The pendulum made clocks more consistent by reducing time lost by roughly 15 minutes and 15 seconds per day. The pendulum represents an adiabatic process in which energy by way of heat is not added or lost in the system. However, work is being done as a result of gravity. Before swinging, the pendulum has potential energy, and as it swings, potential energy is transformed to kinetic energy.
So I'm Jonathan. We created our pendulum with paper, and then we taped it around so it could hold our batteries. Our batteries are our weights in this scenario. Then we cut our hole, and then we used floss as our rod for our pendulum. You drop the weights in here, right? And this is just an example. We're gonna also put it in a stationary position, so my hand is not counted as energy. But the pendulum will never reach this drop point again if energy is not added, and it will eventually stop. When it stops, it will reach its equilibrium position.
This is a great example of the law of conservation of energy. Energy is never created nor destroyed, which seems to be a very big important part when studying thermodynamics.
Let's show them the free body diagram.
That sounds great. So, to reiterate, furthermore, we may have touched on this, but we just really want to get the message home. Right here, as Jonathan described, this would be the starting point where the max peak of energy will be. This is the potential energy. Once it's released, we will never reach this peak point again because energy will be dissipated in the form of kinetic energy. Eventually, the kinetic energy is dissipated, and our pendulum will reach equilibrium, where it will no longer be oscillating back and forth.
Alright, with the conditions that we have, this is as no energy as possible as it's going to get. The airflow may affect it a little bit in the room, but I have no power with it, no energy with my hand, so we're going to do a drop test to see if this actually works. So we're bringing it to a high point here. As long as my wingspan goes, we're going to drop it and see if it gets back to my hand. 1, 2, 3. As you can see, not coming back to my hand. And we'll let it keep swinging just to show you. It's going to keep slowing down until it reaches an equilibrium position. My hand's still all the way over here.
Hi, my name is Derek, and today I'm going to be talking about the entropy balance of our system. So here I'll be talking about the entropy balance for our system. So for our system, we have our entropy in minus our entropy out plus the entropy generated in the universe is equal to the total entropy of the system. And for all systems, your entropy generated has to be greater than or equal to 0. We can also write this in its rate form. Entropy in, the flow of it, flow of the entropy out. It's the flow of the entropy generated equal to the flow of the total entropy of the system. For our case, we'll be working with steady state, so this will be 0. So now here, for the components of the entropy going in and the entropy going out, there's two components. There's the mass component and then the heat component. So here we have the heat flow going in over the temperature of the boundary at the point where it goes in, plus the mass flow going in times the specific entropy going in, dictated by small s compared to big S. And then here we have the same, but for going out. Heat flow going out, temperature of the boundary, point where it goes out. The mass flow going out, specific entropy going out, plus our S generated, and now it's equal to 0. For adiabatic process, which is what we're going to do using for our pendulum, this all will be approaching 0. In which case all we'll be left with is our S-gen. So in the end we have our total entropy generated in the universe, the rate of, equal to 0, which is usually unlikely in real circumstances, but for our ideal process, this is the case.
Hi, I'm Jason. I'm going to explain some of the modern uses of pendulums. So one of the earliest uses of pendulums is in clocks, specifically the grandfather clock, which they added the pendulum to keep the BPM of about 60 seconds for time. And later on, they used the similar idea in metronomes, but for music, where they could change the length to get different BPMs out of it, going closer for faster BPMs and farther for higher lower BPMs. One of the more modern ones is in seismometers, where they use a pendulum attached to a large mass to feel the vibrations of an earthquake to show when an earthquake is about to happen and hit an area. And along with the earthquakes, they also use pendulums in the upper floors of skyscrapers to try and add counterbalance to the weight as an earthquake hits the building. Another more fun use case of a pendulum is in swings in parks. So it uses a similar idea to most pendulums, and it has the kid be the one putting in the work to make the swing go higher and faster. And the difference in the length of the swing can change how far and how fast it can go.
The swing would also not continue unless the kid is adding the energy in. Eventually, it'll reach equilibrium if the kid does not add any more energy in, and they will be very sad. Additionally, their parent could add the energy in and push them, therefore making the kid happy. That is a good example of the conservation of energy in a practical day-to-day use.
Alright, here we have an example of a pendulum. However, this pendulum differs from the pendulum that we just did in our experiment because one, not only is gravity affecting this pendulum right now, it is also powered by a battery. Therefore, this pendulum will continuously keep moving. However, if you notice with our pendulum, the pendulum eventually came to its equilibrium point because the only thing acting on it was gravity, the force of gravity.